Galaxies are considered the largest building blocks of the universe and are massive star systems. These cosmic structures contain billions of stars, interstellar gas and dust clouds, as well as dark matter. Each galaxy, in addition to stars, also contains large amounts of gas and dust surrounding and interacting with these stars. The sizes, star counts, and masses of galaxies vary greatly. The smallest ones are called dwarf galaxies, typically containing a few billion stars. On the other hand, supergalaxies can host millions or even billions of stars and are among the largest structures in the universe. Galaxies form the basic units of the vast structures observed in the sky and play a crucial role in understanding the overall structure of the universe. They serve as important laboratories for observing processes such as star formation, galaxy evolution, and galaxy interactions throughout cosmic history. The structure of a galaxy is formed by the interaction of various components, and these components determine the overall dynamics and shape of the galaxy. At the center of galaxies, there is usually a massive black hole. This black hole lies at the core of the galaxy's gravitational pull and influences the movements of stars within the galaxy. The black hole maintains the structural integrity and dynamic balance of the galaxy. The stars and other galactic components in the vicinity of the central black hole are subject to strong gravitational interactions. The interstellar space of galaxies is filled with gas and dust clouds. These materials appear in different forms in various parts of the galaxy and play a critical role in star formation processes. Gas and dust clouds form the interstellar medium, providing the foundation for the formation of new stars and planetary systems. Stars are born, live, and die within these galactic clouds, playing a significant role in the galaxy's evolution. Another essential component that influences the overall structure of galaxies is the invisible matter known as dark matter. Dark matter forms a halo-like structure around galaxies, enhancing their gravitational effects and helping maintain their structure. Dark matter provides large-scale structural integrity for galaxies, directing the movements of stars, gas clouds, and other galactic components. Although it cannot be directly observed, dark matter plays a significant role in the gravitational effects of galaxies. The combination of these components creates the diversity and complexity of galaxies. Each galaxy houses these fundamental structural elements in its unique arrangement, forming cosmic structures in the universe. Galaxies interact both individually and in groups, shaping the overall structure and dynamics of the universe through galaxy clusters and superclusters. Galaxies as cosmic structures are classified into three main types: spiral, elliptical, and irregular galaxies. Each galaxy type represents different structural and dynamic characteristics in the universe, reflecting the diversity of galaxies. Spiral galaxies are one of the most common and recognizable galaxy types in the universe. These galaxies possess a distinctive spiral structure with well-defined arms and a central core. They are often targets of interest in astronomical observations due to their striking beauty and intricate structures and are an important part of the universe's vast structural variety. The primary structural features of spiral galaxies include a clear spiral arm arrangement and a central core. At the center lies a dense, bright core, often composed of older stars and home to the galaxy's strongest gravitational field. Surrounding the core, spiral arms stretch out, typically containing young star clusters, gas, and dust clouds. These arms extend outward from the galaxy's center, forming its characteristic spiral structure. The arrangement and shape of these arms can vary depending on the galaxy's type and evolutionary stage. Spiral galaxies are typically classified into three main subtypes: normal spiral galaxies, barred spiral galaxies, and irregular spiral galaxies. Normal spiral galaxies feature a distinct spiral arm structure, with the arms radiating smoothly from the center and forming the overall shape of the galaxy. Barred spiral galaxies possess a long, bar-shaped structure at their centers, which supports the spiral arms and facilitates the rotation of stars and gas around these features. Irregular spiral galaxies exhibit a less orderly spiral arm arrangement, often with random patterns far from the central core. Spiral galaxies are among the regions where star formation is most intense. The spiral arms contain young star clusters and large gas clouds, indicating active star formation. These star-dense regions form the bright, colorful sections of the galaxy. The intensity of star formation in these areas provides crucial insights into understanding the dynamic processes and evolutionary stages within the internal structure of spiral galaxies. Gas and dust clouds support the formation of new stars and star clusters, leading to continuous changes in the galaxy's overall structure. As a building block of the universe, galaxies play a significant role in cosmic evolution. The development of the spiral structure varies depending on the galaxy's age, mass, and interactions with other galaxies. Spiral galaxies typically evolve due to galaxy interactions and collisions. Galactic collisions and mergers can alter the spiral structure, rearrange the arms, and affect the star formation processes. These interactions determine the structural characteristics of the galaxy's evolution and long-term changes. The observation of spiral galaxies is one of the most fascinating and informative areas of astronomy. These galaxies offer valuable laboratories for both observations and theoretical studies. Examples such as the Milky Way, Andromeda, and Messier 31 play a critical role in our understanding of the structure and evolution of spiral galaxies. Our own galaxy, the Milky Way, is one of the best-known and most closely studied examples of a spiral galaxy. It is approximately 100,000 light-years in diameter and 1,000 light-years thick. The Milky Way contains a large central core and four major spiral arms: the Carina arm, the Perseus arm, the Scutum Centaurus arm, and the Sagittarius arm. These arms extend broadly from the central core, forming the overall structure of the galaxy. The central core contains dense, old stars and possibly a massive black hole. The spiral arms are filled with young stars, gas, and dust clouds, making the Milky Way a highly dynamic and active galaxy. The Andromeda Galaxy is another significant example of a spiral galaxy and is the closest large spiral galaxy to the Milky Way. Located approximately 2.5 million light-years away, it is part of the same galaxy group as the Milky Way. Andromeda contains a large central core and broad, well-defined spiral arms. This galaxy offers us a chance to study different structures and evolutionary stages of spiral galaxies. Observations of Andromeda provide information about the galaxy's stellar density, the structure of its arms, and its interactions with nearby dwarf galaxies. Andromeda is also on a collision course with the Milky Way, and it is predicted that they will merge in about 4.5 billion years, which will play a key role in understanding large-scale galactic interactions. Messier 31, another name for the Andromeda Galaxy, holds a significant place in astronomical observations. It is one of the few spiral galaxies visible to the naked eye and is frequently observed by amateur astronomers. Like the Milky Way and Andromeda, Messier 31 contains a large central core and well-defined spiral arms. This galaxy is an excellent example for studying the structural properties of spiral galaxies in star-forming regions. Additionally, observations of Messier 31 help us understand the dynamic structure and star movements within galaxies. Other significant examples used in the observation of spiral galaxies include NGC 1300 and NGC 1365. These galaxies are particularly notable for their bar-shaped spiral structures and the arrangement of their arms. NGC 1300 is an excellent example of a galaxy with a central bar and an orderly spiral arm structure. NGC 1365, on the other hand, displays a combination of a bar-shaped structure and well-defined spiral arms. These galaxies help us understand the diversity and evolutionary dynamics of spiral structures. Elliptical galaxies, as the name suggests, generally have a round or oval shape with a more regular distribution of stars. These galaxies typically contain a vast population of stars, mostly composed of older stars. The structure of elliptical galaxies presents an environment where stars are distributed more uniformly and irregularly. The spaces between stars are larger, and the amount of interstellar gas and dust is generally low. As a result, star formation processes in elliptical galaxies have decreased. Elliptical galaxies are often considered old and mature galaxies, representing the final stages of a galaxy's evolutionary process. Additionally, these galaxies tend to be found in higher concentrations within galaxy clusters, forming part of larger cosmic structures. One of the prime examples of elliptical galaxies is M87, Messier 87. M87 is one of the most well-known elliptical galaxies and is located at the center of the Virgo galaxy cluster. M87 has a broad elliptical structure, with a large central core and a relatively flat distribution of stars surrounding it. A supermassive black hole exists at the center of M87, and in 2019, the first ever image of a black hole was captured from this galaxy by the Event Horizon Telescope. This observation marked a significant milestone in our understanding of the nature and size of black holes at the centers of elliptical galaxies. Another important example of an elliptical galaxy is NGC 5128, also known as Centaurus A. Centaurus A is a highly distinctive elliptical galaxy with strong radio emissions. The galaxy contains a large supermassive black hole at its center, and around this black hole is a wide gas disk. Centaurus A serves as a critical model for studying the internal structures and dynamics of elliptical galaxies. Irregular galaxies are galaxies that do not have a defined structure or symmetry, with stars and gas clouds scattered in a disordered manner. Unlike spiral or elliptical galaxies, they lack a distinct center or orderly arm structure. Irregular galaxies often contain regions of young, active star formation, making them important examples for understanding dynamic processes in galaxy evolution. These galaxies can be found in various forms and offer valuable insights into the different stages and interactions of cosmic structures. Irregular galaxies, as the name suggests, do not exhibit a regular structure. These galaxies generally have a lower mass, with stars and gas distributed irregularly. They often contain young star-forming regions and large gas clouds, making them active sites for star formation. The irregular distribution of stars and gas can be the result of galaxy collisions and mergers, and these galaxies offer critical insights into the processes of galaxy evolution. One of the most well-known examples of irregular galaxies is the Large Magellanic Cloud. The Large Magellanic Cloud is a satellite galaxy of the Milky Way and is approximately 160,000 light-years away. This galaxy does not have a distinct central structure or a regular shape. Instead, it features a scattered distribution of stars and gas. The Large Magellanic Cloud is filled with young stars and vast gas clouds, making it a highly dynamic and active galaxy. Observations of the LMC provide important information about the star formation processes and structural dynamics of irregular galaxies. The Small Magellanic Cloud is another example and is also a satellite of the Milky Way. Located about 200,000 light-years away, the SMC has an irregular structure and is notable for its young star-forming regions and star clusters. This galaxy exemplifies the structural diversity and cosmic evolution of irregular galaxies. Another notable example is NGC 1427A, located in the Eridanus constellation, which exhibits a highly irregular structure. NGC 1427A is used as a model for studying the effects of galaxy collisions and the structural changes in irregular galaxies. Observations of NGC 1427A provide significant insights into the impacts of galactic interactions and mergers on irregular galaxies. Irregular galaxies, with their young star-forming regions and large gas clouds, are critical to understanding the dynamic processes of galaxy evolution. These galaxies may form as a result of galaxy collisions and mergers, contributing to their irregular shape. Furthermore, irregular galaxies offer essential information about the flow of gas and matter between galaxies, star-forming regions, and cosmic influences. They play a crucial role in understanding the various stages and processes of galaxy evolution. These three primary types of galaxies reflect the cosmic diversity of the universe, helping us understand the formation, evolution, and structures of galaxies. Each galaxy type contains different structural characteristics and dynamic processes, making them vital to cosmic observations and research. Dwarf galaxies are among the smallest and least massive types of galaxies in the universe. These galaxies typically consist of only a few million stars and represent the smallest examples of the diverse sizes and shapes observed in the universe. Dwarf galaxies show unique characteristics compared to larger galaxies and play an essential role in understanding the building blocks of the universe. Dwarf galaxies are much smaller than large galaxies, with diameters typically around a few thousand light-years, and they contain only a few million stars. Instead of large and visually striking structures, they are often seen as more compact and scattered star clusters. Structurally, dwarf galaxies tend to exhibit irregular patterns rather than the well-defined spirals or ellipses found in larger galaxies. The stars in dwarf galaxies are generally distributed randomly around the galaxy's center. Dwarf galaxies differ significantly from larger galaxies in terms of mass and star count. These galaxies are typically composed of older stars, and their rate of star formation is much lower than that of larger galaxies. Additionally, dwarf galaxies often contain very little gas and dust, further limiting star formation. However, some dwarf galaxies may still harbor active star-forming regions in young star clusters, though this is relatively rare. Dwarf galaxies are frequently found in close interactions with larger galaxies. Due to the gravitational influence of large galaxies, dwarf galaxies often exist as part of galaxy clusters or superclusters. These interactions can influence the evolution and structure of dwarf galaxies. Specifically, the gravitational forces of larger galaxies can alter the structure and stellar distribution of dwarf galaxies. When located near massive galaxies, dwarf galaxies may experience tidal forces that can cause them to be drawn into or absorbed by their larger counterparts. Dwarf galaxies are strongly associated with dark matter. Dark matter increases the gravitational effects of galaxies and helps maintain their structural integrity. In dwarf galaxies, dark matter constitutes a significant portion of their overall mass, helping to stabilize their structure. For this reason, dwarf galaxies are important laboratories for studying dark matter and understanding its distribution and effects in the universe. Dwarf galaxies provide insights into the early stages of the universe. These galaxies have existed as small and simple structures since the formation of the universe. Dwarf galaxies help us understand how galaxies evolved and grew from the early stages of cosmic history. Additionally, they provide information on how small galaxies contribute to the formation of larger galaxies and how they interact during galaxy mergers. Galaxies are dynamic structures, constantly undergoing change and evolution. This evolutionary process encompasses the transformations galaxies have undergone from their inception to the present, including factors like star formation and intergalactic interactions. Galaxies are born as young and dynamic structures in the early universe, during a period characterized by abundant gas and dust clouds and high star formation rates. Young galaxies typically have high rates of star formation, with dense gas and dust clouds that fuel star formation, increasing the galaxy's mass and shaping its structure. The birth, evolution, and death of stars are key factors that determine a galaxy's identity and overall appearance. However, after millions of years, the star formation rates in galaxies can decrease, marking an important phase in the galaxy's evolutionary process. The reduction in star formation is often associated with the depletion of the galaxy's gas and dust reserves. As stars age, significant changes occur within the structure of the galaxy. Young stars are gradually replaced by older ones, transforming the galaxy into a more mature and less dynamic structure. During this period, the galaxy's core typically houses a large black hole, while the outer regions feature increased interstellar voids. The galaxy may eventually exhibit a structure characterized by older stars and a declining star formation rate. Intergalactic interactions and collisions play a significant role in galaxy evolution. When two galaxies collide, massive gravitational interactions occur during the process. The collision can disrupt the structural integrity of the galaxies and trigger new star formation. This process leads to a rearrangement of the galaxy's internal structure and alters its external appearance. Collisions and mergers can increase the galaxy's mass and affect its morphology, leading to the formation of new structures. Such interactions are considered essential factors in the growth processes of galaxies. Galaxy superclusters are the largest and most extensive structural units of galaxies in the universe. These cosmic structures consist of many galaxy clusters coming together to form a colossal organization, playing a critical role in understanding the large-scale structure of the universe. Galaxy superclusters contain millions of stars and galaxies, making them an impressive component of the cosmos on a vast scale. Galaxy superclusters are formed through the gravitational interactions between galaxies and galaxy clusters, which result in large structures. These superclusters are typically found in regions where galaxies are densely clustered and are shaped under significant gravitational pull. Superclusters form a cosmic web of filaments and voids, offering important insights into how galaxies are distributed on a large scale and how they contribute to the universe's overall structure. A galaxy supercluster generally consists of many galaxy clusters grouped into a single massive structure. Galaxy clusters are smaller cosmic building blocks that contain many galaxies, and when they come together, they form superclusters. These clusters are held together by strong gravitational forces, and superclusters reveal how galaxies are organized on a large scale within the cosmos. Superclusters evolve continuously through the merging, interaction, and rearrangement of galaxies. An example of a galaxy supercluster is Laniakea supercluster. Laniakea is one of the largest superclusters in the universe, containing approximately 100,000 galaxies and stretching about 520 million light-years in diameter. The Laniakea supercluster includes the Milky Way galaxy and demonstrates the large-scale motions and distributions of galaxies. The formation and evolution of galaxy superclusters play a critical role in understanding the large-scale structure of the universe. These structures reveal how galaxies come together on a grand scale, the role of gravitational interactions, and the formation of cosmic networks. Additionally, superclusters provide essential information about the expansion of the universe, the movements of galaxies, and their interactions throughout cosmic history. Large cosmic structures in the universe are the result of galaxies, galaxy clusters, and superclusters coming together to form enormous organizations. These structures define the general organization of the universe, revealing the distribution of galaxies and cosmic networks. Large structures are fundamental to understanding the large-scale organization of the universe and the relationships between galaxies. Galaxy clusters are defined as large structures made up of galaxies grouped together. These clusters typically contain anywhere between 50 and 1,000 galaxies. Galaxy clusters are gravitationally bound to each other and often contain large amounts of hot, ionized gas, which emits X-rays, allowing the detection of clusters. Galaxy clusters create significant gravitational effects on a cosmic scale, evolving through galaxy mergers and interactions. A well-known example is the Virgo cluster, one of the closest and best-studied galaxy clusters, containing around 2,000 galaxies. Galaxy superclusters, on an even larger scale, are structures that can span millions of light-years and contain many galaxy clusters. These vast organizations of galaxies and galaxy clusters are gravitationally bound and form part of a cosmic web made up of filaments and voids. Superclusters provide a view into how galaxies are distributed on a large scale and play a crucial role in the structural organization of the universe. The Laniakea supercluster is an important example, containing approximately 100,000 galaxies. Cosmic filaments and voids are the fundamental components of the large-scale structure of the universe, helping us understand how galaxies, galaxy clusters, and superclusters are organized on a cosmic scale. These structures play a critical role in defining the cosmic web and determining the distribution of galaxies. Cosmic filaments are long, thin, and extensive structures where galaxies and galaxy clusters are gathered. These filaments form the large-scale gravitational networks of the universe. Filaments represent the cosmic structures where galaxies and galaxy clusters are connected. These structures help us understand how galaxies are organized on a large scale and how gravitational interactions work. Cosmic filaments are typically regions where galaxies and galaxy clusters are located, showing how galaxies are distributed on a grand scale. Filaments link voids in denser regions, illustrating the gravitational effects between galaxies. These networks show how galaxies come together and help us comprehend the structural organization of the universe. Voids, on the other hand, are the large, low-density regions between cosmic filaments. In these areas, galaxies and galaxy clusters are much more sparsely distributed, and the gravitational effects are weaker. Voids form as a result of the distribution of galaxies and galaxy clusters, playing an essential role in understanding the large-scale structure of the universe. These extensive voids represent the less dense areas in the cosmic web, showing where galaxies are less concentrated. Voids are generally found in the regions where cosmic filaments diverge. Unlike the dense regions where galaxies are tightly packed, voids are characterized by fewer galaxies and weaker gravitational forces. Voids help us understand how galaxies are organized and how gravitational effects vary throughout the universe. Cosmic filaments and voids together define the large-scale structure of the universe and the distribution of galaxies. Filaments show how galaxies come together on a large scale and illustrate how gravitational interactions work, while voids represent the less dense regions where gravitational effects are weaker. These structures help us understand how the universe's cosmic web is organized and provide essential information about galaxy formation and evolution. The universal network structure refers to the wide-scale structures and patterns formed by galaxies and galaxy clusters in the universe. This network plays a fundamental role in understanding how galaxies are organized on a cosmic scale and the large-scale structural features of the universe. The universal network structure consists of various components such as cosmic filaments, galaxy clusters, superclusters, and voids, showing how they interact and shape the large-scale structure of the universe. The universal network structure determines the large-scale movements and interactions of galaxies. Galaxies are connected through cosmic filaments and galaxy clusters, and these structures influence the expansion of the universe and the movement of galaxies. The cosmic web is a dynamic structure shaped by the gravitational interactions and evolutionary processes of galaxies. This web helps us understand how galaxies form, interact, and evolve on a large scale. Galaxy collisions are among the most striking and complex events on a cosmic scale. These phenomena lead to large-scale changes and evolutionary processes within the universe. When two galaxies collide, it profoundly impacts their structure, internal dynamics, and evolutionary trajectory. The effects of such collisions can be observed across a wide spectrum, from the composition of stars to the clouds of gas and dust, and even the sizes of supermassive black holes. The aftermath of galaxy collisions provides significant insights into the structure of the universe and plays a critical role in studying the dynamic processes of cosmic evolution. These collisions can substantially alter the structural integrity and organization of a galaxy. When two galaxies interact, the distance between their stars is typically vast, preventing direct collisions. However, significant changes occur within their internal structures. Interstellar gas and dust clouds can become compressed due to the collision, leading to the formation of large star formation regions. This process can trigger the birth of new stars and clusters. Additionally, the overall structure and morphology of the galaxy are transformed. These alterations may disrupt the spiral structure or lead to an elliptical configuration. During a collision, the gas clouds between galaxies compress and densify. This densification accelerates star formation processes, resulting in the emergence of extensive star formation areas. This phenomenon, known as a starburst, is a typical outcome of galaxy collisions. The formation of new stars significantly alters the appearance and brightness of the galaxy, impacting its total stellar mass and energy output. Furthermore, it also influences the evolution of supermassive black holes at the galactic centers. As galaxies collide, their central black holes move closer together and may eventually merge, leading to an increase in the mass of the black holes and heightened activity at the center of the galaxy. The merging of black holes can release immense amounts of energy and even generate gravitational waves. This process significantly alters the dynamics and structures at the galaxy's core. As a result of galaxy collisions, two or more galaxies may unite, creating a new type of galaxy. These mergers can lead to the formation of elliptical galaxies. During the collision and merging process, spiral structures often become distorted, resulting in more irregular, elliptical forms. Galaxy mergers play a crucial role in the evolution of the universe's large-scale structure, potentially giving rise to larger cosmic formations such as galaxy clusters and superclusters. Additionally, these mergers enhance the gravitational influences of galaxies, strengthening their role within a broader cosmic web. Collisions can profoundly affect the morphology of galaxies. For instance, spiral galaxies may become more irregular or transform completely into elliptical galaxies as a result of such interactions. The events of collision and merging can modify the arms, central density, and overall shape of a galaxy, impacting its overall structure and appearance. The Andromeda galaxy, known as M31 or Messier 31, is the largest and closest spiral galaxy visible to the naked eye. It serves as the nearest major neighbor to the Milky Way and holds significant importance in intergalactic distances. Located approximately 2.537 million light-years away, Andromeda is the most distant large galaxy in the local group. This galaxy exhibits features typical of spiral galaxies, including broad, prominent spiral arms radiating from a central core. The core exhibits a high density, likely housing a supermassive black hole. Andromeda's spiral arms are surrounded by extensive structures containing stars and gas clouds, which contribute to the galaxy's overall appearance. With a diameter of about 220,000 light-years, it is nearly twice the size of the Milky Way. Hosting around 1 trillion stars, Andromeda is the largest galaxy in its group, rich in stellar content. Star formation regions are particularly concentrated along its spiral arms, where clouds of gas and dust facilitate the birth of new stars. The galaxy's center is also characterized by older star clusters and interstellar gas clouds, which play a significant role in its star formation processes and overall brightness. The future evolution of the Andromeda galaxy is particularly important in the context of its interaction with the Milky Way. The collision and merger of two galaxies are expected to occur in about 4 billion years. This potential event could significantly alter the structure of the galaxies involved. Since the distances between stars in the two galaxies are vast, direct star collisions are unlikely. However, the gas and dust clouds within the galaxies may become compressed, potentially triggering new star formation. The outcome could result in the creation of either a new elliptical galaxy or a large spiral galaxy, marking a major cosmic event that will transform the structural dynamics and overall appearance of the galaxies. The Andromeda galaxy serves as a rich source for astronomical observations and research. Telescopes like the Hubble Space Telescope have been utilized to capture detailed images and analyze its structural features. Such observations aid in understanding the distribution of star masses, gas clouds, and black holes within Andromeda. Additionally, it acts as a vital reference point for studying intergalactic distances and cosmic evolution. The Triangulum galaxy, known as Messier 33, is another significant spiral galaxy in the local group. Following the Milky Way and Andromeda, it ranks as the third largest member of this group and provides crucial insights into the building blocks of the universe. Located approximately 3 million light-years away, Triangulum is among the most distant large galaxies visible in the night sky. It is particularly notable for its spiral structure and the stars it contains, with a distinct spiral form. With a diameter of about 60,000 light-years, Triangulum is smaller than both Andromeda and the Milky Way. Its core is surrounded by dense clusters of stars and young stellar formations. The spiral arms extend outward, containing interstellar gas and dust clouds that are filled with star-forming regions and young star clusters. The galaxy boasts around 40 billion stars, making it rich in stellar content. Triangulum is especially recognized for its young star clusters and active star formation areas, which are commonly found along its spiral arms. These regions are known for being sites of ongoing star formation processes. The galaxy also houses older star clusters and vast gas clouds, with new star formation triggered by the collapse of these gas and dust clouds, contributing to the galaxy's structural dynamics. Triangulum plays a significant role due to its relationship with both the Milky Way and Andromeda. Together, these three galaxies form the local group, and their interactions provide valuable insights into galaxy evolution. The future intergalactic interactions and potential collisions involving the Triangulum galaxy may provide insights into its structural evolution. Its relationships with other galaxies serve as a crucial case study for understanding galaxy dynamics and evolution. Triangulum is a rich source for astronomical observations and research. Telescopes like the Hubble Space Telescope have been employed to analyze detailed images and structural characteristics of the galaxy. These observations aid in comprehending the distribution of stellar masses, gas clouds, and star formation regions within the galaxy. Additionally, Triangulum acts as an important reference point for understanding intergalactic distances and cosmic structures. The Sombrero Galaxy, also known as Messier 104, is a striking spiral galaxy that presents a notable appearance in the night sky. It derives its name from its resemblance to a Mexican sombrero hat, thanks to a broad dust band at its center. Located approximately 28 million light-years away, this galaxy is observed as a large and prominent structure in the cosmos. Sombrero Galaxy is frequently studied by both amateur and professional astronomers, making it a significant target for galaxy observations. Sombrero Galaxy features a distinct spiral structure with a diameter of about 50,000 light-years, indicating a rich composition of stars, gas, and dust clouds. Its core is filled with densely packed stars and older star clusters, which stand out in observational studies. One of the most striking features of the Sombrero Galaxy is its central dust band, which obscures a substantial portion of the galaxy's light and accentuates its shape. This dust band encircles the spiral arms and creates a noticeable hat appearance around the bright center of the galaxy. The Sombrero Galaxy contains a prominent central cluster made up primarily of older stars. These stars are densely concentrated at the core, contributing to the brightness of the galaxy's nucleus. Additionally, the spiral arms house young star clusters and active star formation areas, which enrich the galaxy's dynamic structure and provide valuable information about star formation processes. However, the rate of star formation in the Sombrero Galaxy may be lower compared to some other spiral galaxies. At the center of the Sombrero Galaxy lies a massive supermassive black hole, which influences the galaxy's dynamics and governs the movement of stars. This black hole affects the velocities and distributions of stars in the central regions, helping to maintain the overall structure of the galaxy. Furthermore, it is associated with high-energy processes in the galaxy's core, playing a significant role in the evolutionary dynamics of the galaxy. Sombrero Galaxy has been extensively studied through observations made by the Hubble Space Telescope and other major telescopes. Its distinct structure and dust band present important targets for astronomers. Observations yield insights into the galaxy's stellar content, as well as the distribution of gas and dust. Moreover, a detailed examination of the Sombrero Galaxy's dust band provides significant information regarding its structure and dynamics. The Draco Dwarf Galaxy is a dwarf galaxy located in the constellation Draco, recognized as a small yet intriguing structure in the night sky. Due to its diminutive size and low luminosity, it is often observed by amateur astronomers, but it also provides valuable insights for studies on cosmic structures. Positioned approximately 260,000 light-years from the Milky Way, the Draco Dwarf is one of the satellite dwarf galaxies surrounding our galaxy. As its name suggests, it is classified as a dwarf galaxy, containing significantly fewer stars compared to larger galaxies, which results in its low brightness and mass. With a diameter of about 1,200 light-years, it is quite compact. The galaxy lacks a spiral, elliptical, or regular structure. Instead, it is composed of irregularly distributed stars. This structure may hold important clues regarding its evolutionary history and dynamics. The Draco Dwarf primarily consists of older stars, and its rate of star formation is relatively low. While it hosts numerous old star clusters, it is deficient in young stars and active star formation regions. Most of the stars in this galaxy are low-mass stars, which correlates with its overall low brightness and mass content. The dynamics of the Draco Dwarf may be influenced by the gravitational pull of the Milky Way, affecting its structural characteristics. There is no definitive information regarding the presence of a supermassive black hole at the center of the Draco Dwarf Galaxy. However, dwarf galaxies often harbor small black holes. Additionally, the presence of dark matter in these galaxies is a significant area of research. The Draco Dwarf has been examined using various telescopes and observational tools. The Hubble Space Telescope and other major telescopes have provided detailed images of its stellar content and structural features. The Ursa Major galaxy, known as NGC 6217 in astronomical literature, is a spiral galaxy located in the Ursa Major constellation in the northern hemisphere. It has a striking appearance in the night sky, making it an important observational target for both amateur and professional astronomers. Situated approximately 60 million light-years away, the Ursa Major galaxy offers significant insights into its structural and dynamic characteristics. With its prominent spiral structure, it is recognized for its expansive spiral arm formations. The galaxy has a diameter of about 100,000 light-years, categorizing it among the larger spiral galaxies. It contains expansive spiral arms that carry the galaxy's stellar content, gas, and dust clouds, forming its overall structure. The Ursa Major galaxy features a distinct dust band, indicating that it is structurally typical of spiral galaxies. The Ursa Major galaxy contains a mix of old star clusters and young stars. The older stars at its center form a high-density structure, while the young clusters and star formation regions in its spiral arms influence the galaxy's dynamics and evolutionary processes. Typically, the star formation rate in this galaxy is quite high, indicating an abundance of young stars and active star-forming areas. These regions are crucial factors that affect the galaxy's brightness and overall structure. At the heart of the Ursa Major galaxy lies a massive supermassive black hole. This black hole plays a significant role in shaping the galaxy's dynamics and the motion of stars. By influencing the speeds and distributions of stars in its core, the black hole helps direct the galaxy's overall structure and evolutionary pathways. Additionally, the inflow of material around the black hole, along with high-energy processes, enhances the activity in the galaxy's center. The Ursa Major galaxy has been studied using various telescopes and observational tools. The Hubble Space Telescope and other large telescopes have provided detailed images of its stellar content, spiral structure, and dynamics. Observations of the galaxy offer insights into star formation processes, stellar composition, and black hole dynamics. Moreover, the structure and dynamics of the Ursa Major galaxy serve as an important example for research on the evolutionary processes of spiral galaxies. The antenna galaxies are two spiral galaxies engaged in a fascinating interaction. Known as NGC 4038 and NGC 4039, these galaxies provide an excellent example for observing the effects of galactic collisions and mergers on a cosmic scale. Due to their striking structural changes in star formation activity, the antenna galaxies hold significant importance in astronomical research. Located about 60 million light-years away in the constellation Aries, these galaxies are in close proximity, exerting immense gravitational influence on one another. The gravitational forces between the galaxies lead to significant alterations in their structures. This interaction disrupts their spiral arms and causes the distribution of stars and gas clouds to scatter. The collision process triggers bursts of star formation and the emergence of new stars. The antenna galaxies are recognized for their complex structures resulting from these interactions. The gravitational pull causes both galaxies' spiral arms to distort and elongate, promoting the concentration of gas and dust and the formation of new stars. During the collision, interactions between the galaxy's cores create high-energy regions and active star formation areas. Additionally, the elongated, wavy structures resembling antennas formed by these interactions give the galaxies their name. The collision of the antenna galaxies stimulates star formation, resulting in a significant burst of new stars. The collision of gas and dust clouds between galaxies leads to the formation of dense star-forming regions. These areas provide high energy and brightness levels in the central regions of the galaxies. Within these regions, energetic events such as the birth of new stars and supernova explosions occur. Each of the antenna galaxies harbors a massive supermassive black hole at its center, playing a crucial role during their interactions. These galaxies serve as significant targets for numerous astronomical observations and studies. The Hubble Space Telescope and other large observatories have been utilized to investigate their impressive structures and star formation regions. The Black Eye Galaxy, also known as NGC 4594, is a striking elliptical galaxy located in the constellation Virgo. It is commonly referred to as the black eye galaxy due to its prominent dark dust lane resembling a black eye at its center. With its captivating appearance and notable structure, it is an important observational target for both amateur and professional astronomers. The black eye galaxy stands out among elliptical galaxies, typically exhibiting a round or oval shape characterized by a smooth distribution of stars. Approximately 60,000 light-years in diameter, it is surrounded by a vast and dense star cloud. At its core lies a large and massive supermassive black hole, which influences the galaxy's dynamics and the motion of stars. The outer regions are populated by relatively old stars. The most striking feature of the black eye galaxy is its broad and distinctive dark dust lane at the center, which partially obscures the stars, creating a prominent black eye effect in its overall structure. This dark material affects the appearance of the high-mass stars and other cosmic structures at the galaxy's core. While elliptical galaxies are generally known for containing older stars, the black eye galaxy also hosts younger stars. The supermassive black hole at the center plays a critical role in the galaxy's structure, influencing the flow of material and the movement of stars. The black eye galaxy is regarded as a significant target for astronomical observations and research. The Hubble Space Telescope and other major telescopes have been employed to obtain detailed images and examine its structural properties. The Canes Venatici I, known as the Large Dog Dwarf Galaxy, is a small and unobtrusive dwarf galaxy located in the Canes Venatici constellation. Classified among elliptical galaxies, it is often considered a member of the local group of galaxies. Dwarf galaxies are important subjects of research as they represent fundamental building blocks of the universe, and the Large Dog Dwarf Galaxy serves as a crucial example for understanding these small galaxies. Discovered in the 1950s, initial observations revealed that this galaxy is surrounded by significant interstellar gas and dust clouds, although it was initially recognized for its low brightness and surface luminosity. The galaxy was first observed by the English astronomer Sir William Herschel, but detailed studies were deferred to later years. The discovery of this galaxy represents a significant step in understanding the dynamics and structures of local group galaxies. The Large Dog Dwarf Galaxy is typically described as having an elliptical structure, characterized by scattered star clusters and low-density gas clouds. It possesses the expected traits of an average dwarf galaxy: low mass, sparse star density, and a small diameter. Measuring about 1,000 light-years across, this galaxy exhibits very low brightness and plays a limited role in the overall dynamics of the local group. Composed mainly of older stars, the general structure of the Large Dog Dwarf Galaxy shows a dispersed arrangement of these stars. Due to the low star density, the overall luminosity of the galaxy is also quite restricted, with distances between stars indicating a wide spread throughout the dwarf galaxy. This galaxy has been observed by astronomers using various telescopes, including the Hubble Space Telescope and other large observatories, to examine its structure, stellar content, and overall dynamics. The Comet Galaxy, officially known as NGC 2300, is a striking elliptical galaxy notable for its interesting structural features and captivating appearance. Located in the constellation Aries, it is considered an important example among the universe's grand structures. The Comet Galaxy typically exhibits characteristics associated with elliptical galaxies, featuring a round or oval shape with a homogeneous distribution of stars. Approximately 120,000 light-years in diameter, it is surrounded by a vast and dense star cloud. A significant portion of the stars within this galaxy is influenced by the supermassive black hole at its center, which dictates the galaxy's dynamics. The central regions are populated with dense star clusters and many older stars. As is common with elliptical galaxies, the outer regions of the Comet Galaxy consist of older, lower-mass stars. It is believed that a large supermassive black hole resides at the heart of the Comet Galaxy, affecting its overall dynamics and stellar movements. This black hole enhances the galaxy's gravitational pull, guiding the motion of stars and other cosmic materials. Hoag's object, known as Hoag's object, is one of the most intriguing and rare galaxy structures in the universe. Discovered in the 1950s, Hoag's object is a striking galaxy characterized by its rare ring within a ring structure. This galaxy is particularly notable for its symmetrical ring design and the young, blue stars that populate its outer ring. Hoag's object exemplifies the features of a classic ring galaxy, consisting of two main components, a central rounded core and a surrounding expansive ring. The core is filled with older, reddish stars and represents a dense stellar community that contributes to the galaxy's overall mass and density. In contrast, the outer ring is composed of younger, blue stars and includes regions of active star formation. The outer ring contains areas rich in gas and dust, facilitating ongoing stellar activity. This ring is well-defined and symmetrically arranged, which complicates the understanding of the galaxy's dynamics, making it a fascinating subject for scientific research. Hoag's object was first identified by astronomer Arthur Hoag in 1950, who relied on classic telescope observations in an era before the Hubble Space Telescope existed. Hoag recognized that the extraordinary structure of this galaxy did not fit traditional classifications, securing its place in scientific literature. The discovery generated significant interest in the astronomical community, as ring galaxies are quite rare. The unique structure of Hoag's object has provided new insights into galaxy evolution and dynamics, contributing to a better understanding of the diversity of galaxy types and their evolutionary processes. The dynamics of Hoag's object differ markedly from traditional galaxy structures. The central core consists of older stars densely concentrated at the center, while the outer ring contains younger stars and regions of star formation. This structural distinction influences the galaxy's dynamic evolution and the distribution of matter within it. Dense clouds of gas and dust in the outer ring promote star formation, leading to observable young star clusters and newly formed stars. These two components play a critical role in understanding galactic dynamics and determining the role of galaxies in the broader context of cosmic evolution. Hoag's object has become an intriguing target for modern astronomical observations and research. The Hubble Space Telescope and other large observatories have been employed to study its structure and content, revealing details about the galaxy's ring-like formation and offering opportunities to learn more about the processes behind ring galaxy formation. These observations have also illuminated the evolutionary history of Hoag's object, enhancing our understanding of galaxy structures overall. Observations of Hoag's object provide critical insights into the processes of galaxy formation and structure, contributing to research on the evolutionary dynamics of such formations. The Large Magellanic Cloud, known as the closest major satellite galaxy to the Milky Way, is an irregular galaxy located in the southern hemisphere. Named after the famous explorer Ferdinand Magellan, it was first observed during his world voyage from 1519 to 1522. This galaxy is one of the few that can be seen with the naked eye and holds significant importance for astronomical observations. The Large Magellanic Cloud exhibits an irregular structure, lacking the distinct features of a typical spiral or elliptical galaxy, and is composed of numerous stars, gas, and dust clouds. With a diameter of about 14,000 light-years, it is recognized as the largest satellite of the Milky Way within the local group. Its internal structure includes a mix of old star clusters, regions of young star formation, and areas of active stellar development. At its core lies a dense region containing both older and younger stars, while the outer areas are typically filled with gas and dust clouds that promote star formation. The internal composition of the Large Magellanic Cloud displays a complex and irregular distribution, making it an intriguing target for various astronomical studies. The galaxy is rich in stellar diversity, showcasing both young and old star clusters on either side. In particular, many older star clusters and extensive young star groups can be found in the central region. The outer parts of the galaxy contain large gas and dust clouds that stand out as regions encouraging new star formation. These star-forming regions include H2 regions, which consist of gas clouds heated by high-energy stars, where the birth of new stars and the evolution of star clusters can be observed. The discovery of the Large Magellanic Cloud dates back to the 16th century when Ferdinand Magellan noted its presence during his voyage. However, detailed information about its nature was not obtained until the early 20th century, when astronomers began conducting more comprehensive observations to understand the galaxy's structure and content. In the 1930s, Edwin Hubble and other astronomers identified the Large Magellanic Cloud as a satellite galaxy orbiting the Milky Way, enhancing the understanding of its dynamic structure and star formation processes. The interactions between the Large Magellanic Cloud and the Milky Way influenced the galaxy's structure and dynamics. Its proximity leads to interactions among interstellar gas and dust clouds, affecting star formation processes. As a result, the Large Magellanic Cloud has become a significant target for many modern astronomical observations and studies. The Hubble Space Telescope and other major telescopes have been utilized to investigate the galaxy's structure and stellar content. The Magellanic Stream, officially known as the Forens Galaxies, consists of two interacting irregular galaxies. These galaxies are particularly noteworthy for their colliding and interacting structures. Often referred to as galaxy pairs or galaxy collisions, the Magellanic Stream exhibits a rich composition of star-forming regions and cosmic gas clouds, offering important insights into galaxy interactions. The Magellanic Clouds consist of two main components, Magellanic I and Magellanic II. Both galaxies are in interaction, characterized by their complex structures and dynamic properties. They were discovered in the 1990s by astronomer Richard S. West and his team, marking a significant step in understanding the effects of galaxy interactions and collisions on galactic structures. West and his colleagues conducted detailed studies of the dynamics and structure of these galaxies, providing crucial insights into how interactions influence galaxy evolution. As galaxies that collide and interact, the Magellanic Clouds serve as important examples for understanding galactic dynamics and interactions. These interactions lead to the compression of gas and dust clouds, accelerating star formation. Additionally, they alter the structure of the galaxies and give rise to new galactic formations. The Whirlpool Galaxy, also known as the Feraldak Galaxy, is a striking spiral galaxy in the universe. It draws attention for its unique spiral structure and its interaction with a smaller neighboring galaxy. Although it cannot be seen with the naked eye, it can be extensively studied using powerful telescopes and observatory equipment. The Whirlpool Galaxy has a typical spiral structure, featuring a dense core at its center and expansive spiral arms. These arms are a defining characteristic of the galaxy's structure, filled with stars, gas, and dust clouds. The core typically contains older, more mature stars, while the spiral arms are rich in young stars and active star formation regions. An interesting aspect of the Whirlpool Galaxy is the small galaxy nearby that interacts with it, influencing its structure and dynamics. This interaction leads to the formation of new stars and the redistribution of gas clouds. The Whirlpool Galaxy boasts an active star formation region, with dense clouds of gas and dust within its spiral arms that promote the creation of new stars. The Magellanic Clouds, officially known as the Forens Galaxies, are two interacting irregular galaxies. They stand out due to their colliding and interacting structures, often referred to as galaxy pairs or galaxy collisions. The Magellanic Clouds exhibit a rich array of star formation regions and cosmic gas clouds, providing valuable insights into galaxy interactions. Galaxy interactions lead to the compression of gas and dust clouds, accelerating the process of star formation. Additionally, these interactions alter the structures of galaxies and give rise to new galactic formations. The Whirlpool Galaxy, also known as the Feraldak Galaxy, is a striking spiral galaxy in the universe. It stands out due to its unique spiral structure and its interaction with a smaller neighboring galaxy. Although the Whirlpool Galaxy is not visible to the naked eye, it can be studied in detail using powerful telescopes and observatory equipment. This galaxy exhibits a classic spiral structure, featuring a dense core at its center and broad spiral arms extending outward. These arms are a defining characteristic of its structure, filled with stars, gas, and dust clouds. The central core generally contains older, mature stars, while the spiral arms are rich in young stars and active star formation regions. An interesting aspect of the Whirlpool Galaxy is the small galaxy nearby that interacts with it, influencing its structure and dynamics. This interaction leads to the formation of new stars and the redistribution of gas clouds. The Whirlpool Galaxy hosts a highly active star formation region, with dense clouds of gas and dust in its spiral arms that facilitate the creation of new stars. High-resolution infrared observations from the James Webb Space Telescope reveal intricate details of the galaxy's internal structures, star formation regions, and galactic interactions. While it's challenging to provide an exact number of galaxies in the observable universe, scientists employ various methods to estimate this figure. Current estimates suggest there are approximately 2 trillion galaxies in the observable universe. This estimate stems from research based on data collected by the Hubble Space Telescope in the 1990s. Particularly, Hubble's Hubble Deep Field and Hubble Ultra Deep Field observations helped in studying galaxies in very distant regions, contributing to our understanding of galaxy density in the universe. These data form a foundation for estimating the distribution and number of galaxies, although Hubble's observations cover only a tiny fraction of the universe, making these estimates representative of just a small sample of the observable cosmos. With a broader array of observatories and advanced telescopes, it becomes possible to obtain more precise data regarding the number and distribution of galaxies. Furthermore, next-generation observatories like the James Webb Space Telescope will continue to explore deeper regions of the universe, validating and refining these predictions. The size and complexity of galaxies provide fascinating insights into the vastness of the cosmos. These colossal structures, each harboring billions of stars and various other cosmic components, play a fundamental role in our understanding of the universe's building blocks and dynamics. The diversity and scale of galaxies challenge the boundaries of science, allowing us to delve deeper into the nature of the cosmos. This vastness and variety ignite human curiosity and the desire for exploration. Comprehending what lies within galaxies, how they formed, and how they evolved remains a perpetual source of fascination for scientists and astronomy enthusiasts alike. The sheer number and size of galaxies in the universe have always captivated humanity. They provoke not just scientific curiosity, but also a profound interest in understanding how the universe operates and our place within this cosmic structure. Investigating these grand cosmic entities represents one of the greatest discoveries in human history, both scientifically and philosophically. The endeavor to unravel the secrets of galaxies reflects humanity's desire to expand its knowledge about the origins and future of the universe. Don't forget to subscribe for new documentaries and more scientific content.